Good morning, everyone. So, in the previous class, we have discussed the development of transfer function for the elements of a control system, this complete control system. Okay, so we started with process transfer function. So, we started with this process transfer function where we derived a mathematical model using the energy balance equation. If you check the previous class, energy balance equations for this heating process. That's what our CSTR process. So after that, we derive the transfer function of the measuring element, where we assume the thermometer behaves as a first order system. Okay, so in the last class, we completed two important elements. So these two, this is one and this is two. That is process transfer function and measuring element of a transfer function. So today we'll continue to the same discussion and derive the transfer function of the controller and final control element. Okay, now let us understand, first let us understand the basic idea of the controller. So in any feedback control system, the controller receives a error signal. What receives? It receives the error signal. So this error defined as the difference between the set point value and the measured value of the process variables. So we define error is equal to TR minus TM, where TR is the set point temperature, TM is the measured temperature. So the purpose of this control is to reduce the error, bring the process variable to our desired set point. Okay, then what is the output? Now let us control produce, what is control output? Control produce the output signal which acts on the final control element. In our heating system, in our heating system example, the final control element is heat input Q to the process. Okay, so here we combine, for the simplification, we make it a control mechanism on control and final control element. It's combination of these two. So now we'll derive a transfer function for this one. Let's see. So now we can assume a controller is proportional controller. We will discuss later on all controllers, but right now just assume the only proportional controller. So the controller output is proportional to the error signal, right? Assume like a controller, the control output is proportional to the error signal. Now let's discuss about this complete control and final control element. So what I mentioned to here, that's what Q is proportional to the error signal because we choose proportional controller. And what we can mathematically write, right? Q is equal to Kc into error plus A, where Kc is proportional gain or controller sensitivity. Proportional or maybe the proportional gain. So here A is the bias value or steady state heat input. Okay. So what exactly the physical meaning of bias value? So let us understand. So now let us understand in the physical meaning of bias value. What is the meaning of this bias value? So when the system reaches steady state, the error becomes 0. That means error equal to 0. So the control output becomes, when it becomes 0, so what exactly here? Now this becomes 0. Then what will happen? Q equal to A. This means that even when the error is 0, a certain steady heat input must be supplied to maintain the temperature. It's very, very important. When error is 0, a certain steady state input must be applied to maintain the temperature. So therefore, the constant A represents the steady state heat input, which also called bias value. Remember, this is very, very important. Okay, then we can write the steady state equation. At steady state, we can write Qs is equal to Kc into Es plus A, the same equation. From here, we can write at steady state, Qs is Q become a Qs, Kc into E become Es plus A. But at steady state, the set point equals to the measuring value. That's what we discuss here. So that's TRS equal to TMS. Yeah, sorry, it's a, yeah. TRS is equal to TMS. Okay, at steady state. Therefore, so now let's write about the deviation form. Let's write in the deviation form. So now we want to convert the equation into deviation variables, which is necessary to before applying the Laplace transform. That's what we discussed number of times. Now let's start from the equation 1. What is equation 1? Q is equal to Kc into epsilon plus A. So, and subtracting the steady state equation, that is Qs is equal to A, we know very well. That's what we discuss. Qs is equal to A. So then A equal to Qs. So now V is equal to Q minus, now Q equal to Kc into epsilon plus A becoming Qs. So now Q minus Qs is equal to Kc into epsilon, or maybe Kc into error. Okay. So now what we'll get? Now Q minus Qs and Kc. We know Q minus Qs will become a capital Q. That is equal to Kc into epsilon. Okay. Or maybe Kc into error. So now apply the Laplace transform. Why? We want to convert the equation into the S domain. That's the reason we're going to do apply the Laplace transform. Q of S is equal to Kc into E of S. Therefore, the transfer function of this control and final control element becomes Qs by this E of S is equal to Kc. So this is the transfer function of the controller and final control element. Simply we call constant gain. That's called Kc. So this represents the proportional controller. This only for P only controller, not PR PAD. Okay. Now let's see the block diagram. So here the error signal E of S enter into the controller. The controller multiplies this error by the gain Kc and produce an output. That's called Q of S, which acts on the process. Okay, so the block diagram represents simply error and then controller and then output. Okay, that's what we'll develop, right? That's what we done till now. Okay, so now what we done till now? Now we have derived the transfer function for the all the individual elements of a control system. What we obtain? We obtain the process, transfer function, then measuring element, then controller and final control element. So let us combine all these transfer functions and represent the complete control system of a block diagram. So to understand this clearly, we should start from the process always. Let us start with the process block. So what we done? In ideal derivation, using the energy balance equation, the process behaves as a first order system. So the transfer from this 1 by tau s plus 1. What is the output? This is T dash of S, which represents the process temperature, also called as a control variable. Then load disturbances. So before entering to the process, there may be disturbance acting on the system. For example, in heating system, the inlet temperature may change. This disturbance is represented as a TAS. So this disturbance is enter the process through a summation junction, where it combines the manipulated variable. Okay. So then we want to discuss about the final control element. So this is what final control, the manipulated variable in the system, that is U of Q of S. Okay. Before entering to the process, the signal processed through the final control element. So the transfer function final control element is 1 by WC. Please go through my previous videos how we got this 1 by WC also. So this is element converts the control signal into the actual heat supply to the process. Okay. Then what about controller? The heat input Q of S is generated by the controller only. So the controller receives a error signal and produce an output to the proportional to error. So for proportional control, the transfer function is Kc. So the controller multiplies the error signal by controlling gain Kc to generate a control signal. Okay, what is error generation here? Okay, that is E of S is equal to TR of S minus TMS of S. So then we know the measuring element, we derive 1 by tau ms plus 1. Okay. So this measured signal is then fed back to the comparator. The completing of the completing the feedback loop. Okay. What is the sequence of this feedback loop? Always remember this, very important. So the sequence of the operating on this control system is, first the process generates the output. What exactly? The process generates the output T of S, and then the measuring element measures the temperature produced of TMFS, then compares with this TRS and TMS, and the error signal EFS is generated. Then control multiplies the error signal by Kc, and then final control element adjusts the heat input Q of S, and then the process receives the input and produce a new output temperature. So this cycle continuously becomes zero, measuring the process temperature reaches the our desired set point. So this block diagram, this is a block diagram, represents the complete closed loop control system of a heating process. That's called CSTR. Okay.